To get started, we'll simply click Tools from the menu and then click on the motion icon. This will launch the Dynamic Designer browser. We can create a new mechanism by right-clicking on Motion Model and choosing New Mechanism. In this particular mechanism, we don't have any assembly constraints defined in Solid Edge. Therefore, we can disregard this window here. The first thing we need to do is to define the moving and ground parts. Had these components been constrained in the Solid Edge assembly, we could automatically have the program determine which were moving and which were grounded. Since we don't have any assembly constraints, the first thing we do is define which will be moving. Holding down the Control key, we can click on the Geneva wheel, the input shaft, and then either click, hold, and drag the parts onto the moving parts branch. Or another way to do it is to right mouse click on those highlighted parts and then choose moving or ground, as we'll do here. We'll right click on the housing and choose ground part. The remaining two components, the drive pin and the sleeve, are part of this input wheel. So we can hold down the Control key, pick those two parts, and simply right mouse click on them, attach to the input shaft. They'll be treated essentially as a subassembly. The next thing we'll do is we'll define our simulation settings and gravity. We can right click on the mechanism name and choose System Defaults. Here we can change the direction of gravity to be in the negative Z direction, which coincides with the global orientation. We can then click on the Simulation button, and we can enter the duration of the simulation and the number of frames. The frames will control the resolution of the plots as well as the video playbacks and the quality of AVI files that we might save. We'll click on the Solver tab and we'll make a couple simple changes that will accommodate this particular simulation. The next thing we'll do is we'll simulate with just gravity active to determine which parts are moving and which parts are grounded, simply to verify what we did earlier. We can stop the simulation immediately by clicking on the same button we started the simulation with. Click, hold, and drag the slider back and forth to replay the animation. We can see that we're in need of some constraints in this assembly. We'll click the Simulate button again to delete the results. We'll begin adding constraints using Dynamic Designer. We can simply right-click on Joints, choose Add Revolute Joint. We'll click on the Geneva wheel, click on the housing, and then click on a circular edge to use the midpoint of that circle as our location. And then we'll simply click on the inside cylindrical face to align the axis of the joint. Select OK and the joint is applied. We'll do the same thing for the input wheel. Right click on Joints, Add Revolute Joint, click the part, click the second part, click a circular edge for the center location of the constraint. And then in this case, we can pick a flat face. It will make the axis of the constraint perpendicular to the face. This particular constraint will also have a motor applied to it. Therefore, while we're still in the dialog box for this particular joint, we'll click on the Motion tab, change the motion type to velocity, and we'll leave the default of 360 degrees per second. We notice that the orientation is going to be counterclockwise. We're interested in reversing the direction and making it clockwise, so we can simply return to the Definition tab, click on the Toggle Direction button, and it will change the direction of the rotation. Next, we'll go ahead and run a simulation to simply verify the input we applied to the motor is correct. We can see that we haven't yet defined a contact between the sleeve and the Geneva wheel. We'll prepare to do this next. First, to verify our input, we can see visually that it looked correct in that it was a constant speed. And to graphically verify, we can simply click on the plus sign next to joints, find the joint where we applied the input to, right-click, choose plot, angular velocity, and we'll choose the z direction. These components are relative to the joint's coordinate system. And we can see that this speed is constant at 360 degrees per second, like we anticipated. Right-click on the white area of the plot and choose Delete. Let's go ahead and delete the simulation results and prepare to define the contact. Before we define the contact, we'll define a rotational damper attached to the Geneva wheel, which will represent some sort of an external resistance on the wheel. Right-click on Dampers, choose Add Torsional Damper. Pick the first component, which will be the Geneva wheel, second component, the housing, and just like we did for the revolute joints earlier, we can select a circular edge to define the center location of the damper, and then a cylindrical face to align the axis of the damper. Then we can define a numerical value to be characteristic of some sort of a resistance on the shaft that would be keyed to this Geneva wheel. Now we'll go ahead and we'll define a contact between the sleeve and the Geneva wheel. We have a couple different methods of modeling contacts in Dynamic Designer. For this method, the simplest way is going to be using a 3D contact. We can right-click on Contact, choose Add 3D Contact, and just simply pick the two parts that will make contact. We can select the Contact tab. We can define the material types for the collisions, and we can turn friction on or off. To start with the basic simulation, we'll model with friction off. We'll go ahead and run the simulation to verify our inputs so far. We can stop the simulation prematurely at any time by clicking the Start button again. Click, hold, and drag the slider to replay the animation. To verify the output of the Geneva wheel, which was one of our objectives of the simulation, we can simply right mouse click on the joint that connects the Geneva wheel to the housing, plot, projection angles, z-axis. These components are relative to the joint's coordinate system. And we can see what that looks like. The components of a plot can be changed by right-clicking on the plot and choosing Axis Properties if we're next to the axis, or if we're in the plot area, we can right-click in the plot and choose Chart Properties. The second objective was to determine the contact force on the drive pin. To plot contact forces, we can right mouse click on the component we wish to see the force for and add result vectors. Since the sleeve was attached rigidly to the input shaft, we need to expand the plus sign next to input shaft and then right mouse click on sleeve, choose Add Result Object, Reaction Forces. If we move the model back to the position where contact was occurring, we'll notice force vectors appearing on the sleeve. Those vectors will increase and decrease in size depending on the value of the force. Not only do we see a graphic representation of the force that's occurring, but we can also plot the numerical values of that force. Down on the reaction force node, we can click the plus sign, find the contact force feature, click, hold, and drag and drop onto XY plots. Here we can see the contact force. We can make an adjustment to this scale by simply right-clicking on the axis, choosing Axis Properties, and making a change to the scale. The third objective of the simulation was to determine the input torque required to cycle this mechanism. A great feature of Dynamic Designer is that we can use the tool as a reverse engineering method to determine input torque requirements and input actuator requirements when they're not known. To plot the motor torque required to cycle the mechanism, we can simply right mouse click on the constraint that had the motor applied to it, choose Plot, Motion Generator, and these are taken relative to the global coordinate system. In this case, it will be the Y direction. Here we have the torque requirements for the input. Another nice feature we have is that we can compare new and old results. For example, if we come down to the XY plots node, expand the plus sign, and then find the new plot that we just created, which was the moment plot, click the plus sign again, and then right mouse click on the revolute joint for that plot, and choose Preserve and Copy. This will preserve the existing curve and allow us to make a change to the model and plot a new curve over the old. We'll go ahead and we'll delete results, and we'll make a model change. In this case, we're going to add friction back to our 3D contact. And then we'll run the simulation again. Immediately, the new results are plotted directly on top of the old. Here we can see the difference between adding friction and not adding friction. Clicking on the plot moves the cursor to that corresponding position, and we can see at which point that friction value is maximum. The last thing we'll do is we'll create a movie file of this animation with plots on the screen. To create an AVI movie of our simulation, we need to first have results active like we do here. Then we can simply right-click on the mechanism name and choose Export AVI Movie. Here we can make changes to either the frame or the time settings to either increase the quality of the AVI file if we have more frames and smaller steps, or reduce the size of the AVI file and slightly reduce the quality by increasing the steps. We can give it a name and location for the file, and then we can save it. And once we click OK, it will start creating the video and animating at the same time.